Hi, for this video we will be talking about sensitivity analysis and how it is related to the theory of duality. In the previous lessons that we had, we were able to discuss how changes in the right hand side of your constraints will affect your optimal solution and eventually affect your z-value. And from there, we were able to come up with what we call a change in z over change in some resource, whatever resource we were talking about. And for this lesson, we will tie them up all together into what we call duality theory. And this is also where uh, I will eventually introduce to you the concept of shadow price, which is one of the fundamental concepts of duality theory, which is very much applied in 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 the sensitivity analysis of linear programming models. Okay, so discussing duality theory requires a certain frame of mind. What is this frame of mind that is needed in order to understand duality theory? Well, first, when we talk about objective functions, our objective functions, either minimization or maximization, should be seen either as cost functions or benefit functions. If your if your objective is to minimize, then your objective function can be seen as some cost function. No? However, if your objective is to maximize, then the function associated with this objective can be seen as some form of benefit. No? Something that is good we would like to maximize, something that is bad or something that has a cost we would like to minimize. Now, for our constraints, we generally have three kinds of constraints: greater than or equal to, less than or equal to, or equality constraints. If you have a greater than or equal to constraints, we generally see them, we generally see them as some sort of demand requirement constraints. If your constraints are less than or equal to constraints, then we see them as supply constraints, constraints that have a maximum amount of supply. And finally, if your constraints is an equality constraint, then they can be seen as both demand and supply constraints. I hope the last one is very obvious because, as you may remember in math, if you have an equality constraint, you can actually split them up into the intersection of a less than or equal to and a greater than or equal to constraint. And that is why an equality constraint is seen both as a supply constraint and a demand constraint. Okay? Next, this frame of mind also requires us to see decision variables as some form of economic activity. Okay? These are activity that either produce some benefit, and that is why you are maximizing the benefit function, or this economic activity produces some cost or incurs some cost, and that is why we'd like to minimize the cost function. At the same time, the left-hand side coefficients of your constraints are seen as activity consumptions or activity contribution, depending on how the constraint is written. Let me give you an example. In the in the red blue gadget problem, we have the constraint 2x1 less than or equal to 1000. And if you remember, this pertains to the steel supply of the company. Okay, this particular coefficient 2, as we can see, is the coefficient of a less than or equal to constraint. And in this case, a less than or equal to constraint is a supply constraint, and therefore the coefficient is seen as an activity consumption. And let's try to understand that in this context. what is this 2 in relation to x1 and 1000? In this case, 2 is the activity consumption of steel when you produce X1 or when you produce red gadgets. Okay? In the same way, if you look at your wood constraint, you have your 2x2 less than or equal to 1000. Sorry, 1200. This left-hand side constraint is an activity consumption of wood by x2. And if you want to complete the analysis, if you look at the labor constraint, 3x1 plus 2x2 less than or equal to 1/8, this 3 is how much each x1 consumes from your labor supply. So kada x1 that you produce, it consumes 3 units of this right-hand side, which in this case is labor. And this 2 is how much each x2 consumes from your in your labor or from your labor supply. Okay? Now, what if your constraint is a greater than or equal to constraint? And let's say your constraint looks like this. Some random constraint 2x1 plus 3x2 is greater than or equal to 100. And let's say this 100 is a vitamin A requirement, meaning you need to get at least 100 units of vitamin A. Okay? So in this case, this coefficient 2, okay, is the coefficient of an is the coefficient of a demand constraint. And in this case, the coefficient of a demand constraint serves as an activity contribution. Now, what does this mean? This means that for every unit of x1 or for every economic activity x1, let's say x1 is the act of buying a certain fruit, let's say. Whenever you buy a piece of that fruit, x1, that fruit contributes 2 units of vitamin A to this requirement. And let's say x2 is let's say this is buying apple. This is buying apple, and let's say and this is buying oranges. So the act of buying oranges contribute 3 units of vitamin A to your requirement. And that is why the left-hand side coefficient can be seen as either an activity consumption or an activity contribution, depending on the kind of constraint you have. Now, before we move on to the main lesson of duality theory, let me first explain and define 2 words that we will be using often when we deal with sensitivity analysis. The first word is called relaxation, and the other word is called tightening. So let me define relaxation first. What is relaxation? Relaxation is the process of changing the linear programming model such that the result of this change will result to either the optimal value staying the same or be better. Okay? So a change in your linear programming model is a relaxing change if the result of this change results to your optimal value either staying the same, so nothing happened, or it will get better. And in this case, getting better is relative because it depends on your objective. Getting better, if you have a maximization model, means that your z will go up, will increase. Getting better in a minimization model means that your z will go down or decrease. On the other hand, if the change in your linear programming model is a tightening change, then what does that mean? That means that this change will result to either your optimal value staying the same or worsen. And obviously, worsen is the opposite of what we discussed of opposite of getting better, no? So if your objective is to maximize, your value will worsen if the value will decrease. And if your objective is to minimize, then the objective function value will worsen if your value will increase. There are a lot of changes that can happen in your linear programming model, and the following slides, the next, I think, 3 slides, will show you different ways in which you can change your linear programming model. For this slide, we are talking about changes in the right-hand side coefficient. So if you remember your dead blue gadget problem, so you have your 2x1 less than or equal to 1000, 2x2 less than or equal to 1, 2, and 3x1 plus 2x2 less than or equal to 1, 8. And in this case, we are talking about changes in your right-hand side. So whether you increase or decrease your right-hand side. Okay? Now, if your constraint is a supply constraint and the right-hand side increases, then that is a relaxing change. Let me explain that. For example, let's take the first constraint. No? Let's say 2x1 less than or equal to 1000, and we increase this to 1200. Now, because your right hand side increased, so originally your 2x1 less than or equal to 1000 gave us, simplified, gave us an x1 less than or equal to 500. However, because we changed the right hand side to 1200, then the constraint becomes an x1 less than or equal to 600. And obviously, graphically, if this is your x1 less than or equal to 500, then an increase by 200 here will result to a shift of this line to the right, and therefore you're adding this area in which the linear programming model can find or may find a better solution, no, nadagdagan ng feasible region, and therefore we have more options at our disposal, and therefore it is very possible that the linear programming model may find a better solution. If the linear programming model cannot find a better solution in this added area, then the optimal solution will stay the same, meaning z is equal to 295,000. However, if the linear programming model is able to find a better solution here, then obviously our z value will increase. And that is why if you have a supply constraint and your right hand side increases, you are relaxing the model. And if you remember, what does relaxing mean? It means that your optimal value will either stay the same because the linear programming model cannot find a better solution when you added the feasible region, or if it can find a better solution, then the optimal value will be better. Okay? And conversely, if your constraint is a supply constraint and your right hand side decreases, obviously it will be a tightening process, because in this case, you are reducing your feasible region. So as you can see, if this is your 2x1 less than or equal to 1000, and let's say you decrease this to 800, then that becomes an x1 less than or equal to 400. So originally your shaded area is here, okay? And but because you decreased the right hand side to 800, therefore this line shifts to the left, and let me use red. This line shifts to this line where an x1 is equal to 400. And what happens here is you are actually removing this part of the feasible region. Okay? And because you are removing a part of the original feasible region, it is very possible that the optimal solution is affected. And because the optimal solution is affected, the linear programming model is forced to look for uh, a new optimal solution that is worse. No? However, it is also possible that by removing this red area, the optimal solution is not affected, and therefore your optimal value stays the same. And that is why, if your constraint is a supply constraint and your right hand side decreases, it is a tightening process. If you remember, tightening means your optimal value either stays the same, meaning your optimal solution was not affected by the reduction of the feasible region, or if it is affected by the reduction of the feasible region, then the optimal value will worsen. And if your constraint now is a demand constraint, then the opposite will just happen. Okay? I will leave it up to you to understand this. If your demand constraint is a demand constraint, it will tighten if your right hand side increased. It will relax if your right hand side decreased. Now, if we are now talking about changes in the left-hand side coefficients, then we have this table. Okay? And let me discuss that this way. So again, let's say we have our red-blue gadget problem, and we're talking about the steel constraint again. So 2x1 less than or equal to 1000. And because we're dealing with left-hand side coefficient changes, then what we are saying is we are trying to see what will happen to your model if we are changing this coefficient. And let's say this coefficient became 3. Okay? Remember our discussion of the definition of left-hand side coefficient. Our left-hand side coefficients are either activity consumption or activity contribution, depending on the kind of constraint. And because this is a less than or equal to constraint, which is a supply constraint, then we can see this as an activity consumption. For every x1 that you do, x1 consumes 2 units of whatever this 1000 is. And because we are increasing 2 to 3, then this increases the activity consumption. And because this increases the activity consumption, the best case is your optimal value will not be affected, and therefore your optimal value will be the same. However, worst case is your optimal value will be affected because tumaas yung consumption, and therefore your optimal value will worsen because you're consuming more of a particular resource. And that is why if you have a supply constraint and your left hand side increases, then it is a tightening process. On the other hand, if the left-hand side decreases, then your activity consumption decreases. Therefore, it is a tightening. Sorry, relaxing change. Conversely, if your constraint is a demand constraint, therefore your left-hand side coefficients are activity contributions, then if these contributions increase, then you are relaxing your model. If your contributions decrease, then you are tightening your model. Why is it that if your contribution increases, you are relaxing the model? When you increase the contribution of a certain activity to the requirement, this tells us that it's easier to meet the demand requirement. And because it is easier now to meet the demand requirement, then this gives us a sense of relaxation to the model. No, you are making it easier for the model to reach a certain requirement, and therefore it's a relaxing. If, however, you are decreasing the activity contribution, then what you're actually doing is you're making it harder for the model to reach the requirement, and therefore it is a tightening model, tightening change. Now, for changes in the objective function coefficient, then we are now talking about changes in your objective, which is to maximize z equals 500x1 plus 300x2. And in this case, we are dealing with changes on the coefficients 500 and 300. Obviously, if this increases, and because your objective here is to maximize, then your z value also will increase. However, if your objective is to minimize, then if your objective function coefficient increases, then um, this z value will also increase. But because your objective is to minimize, then technically you are worse off. Okay, and that is why, if your constraint, if your objective, sorry, this is not constraint. This has to be objective. If your objective is a maximization and your coefficient increases, then technically we can say that you will be better off, or your optimal value will be better. Consequently, if your objective is to maximize and your coefficient decreases, then obviously you will be at a worse situation. Conversely, if your objective is to minimize and your coefficient increases, then you will be worse off. And if your objective is to minimize and your coefficient decreases, then you will be better. Do note that in this table, I didn't use the words tightening and relaxing. Why? Because changes in the objective function does not affect your feasible region. If your constraints look like this, okay, no matter how these two changes, it will not affect your feasible region. And therefore, you cannot technically say that your model tightened or relaxed. Because in this case, the only time you say the model is experiences a tightening process is when your feasible region, in this case, gets reduced. And at the same time, you can only say that a change is a relaxing change is if your feasible region increases. Okay? Now, what if you are adding a constraint? So let's say we have this feasible region, and let's say we have three constraints. and the feasible region is this. Okay? And let's say you forgot to add a fourth constraint. Okay? Adding a constraint, whatever the constraint is always a tightening process. Why? Let me give you an example. Let me give you the more obvious reason. If, let's say, you forgot a constraint, and let's say the constraint looks like this, okay? What is happening here is you are technically removing this part of the feasible, this part of the feasible region. Because your feasible region got reduced, then obviously it is a tightening process. Okay? However, however, let's say, okay, however, let's say, so let's put back the original original constraint. Let's say you forgot a constraint, but the constraint looks like this. Okay? And because the constraint looks like that, then this feasible region was not affected. And therefore, because the feasible region was not affected, then your optimal value will stay the same. And that is why adding a constraint will always be a tightening process, because if you remember, a tightening change means that your optimal value either stays the same because the additional constraint did not affect the feasible region, or your optimal value will worsen because the additional constraint affected the feasible region, and at the same time it affected the optimal solution, which means that you are forced to look for a worse solution, taking into consideration the new constraint. Okay? And that is why adding a constraint will always be tightening. On the other hand, adding a decision variable is always a relaxing change. And why is that? Let me explain it this way. So let's say your feasible region looks like this. Okay? So it's a two-dimensional feasible region. Okay? And let's say this is your x1 and this is your x2 axis. Okay? Now, because you are adding a third variable, x3, let's say x3, you are technically adding a third dimension. And because you are adding a third dimension, then let me use red, then you are technically, for example, you are technically adding this feasible region, this feasible region. Okay? You are adding a third dimension, which means you're adding feasible region. And because you are adding feasible region, then technically your model will have more options. And because you have more options, then it is possible that your model will be able to find a better solution. And because it is possible for your model to find a better solution, then it is a relaxing. If in the additional feasible region you cannot find a better solution, then the optimal value will stay the same. However, in the event that you can find a better solution in the added feasible region, then obviously your optimal value will be better. Okay? And that is why always you adding a decision variable is a relaxing process.